In this lecture, let's talk about transformer architecture. Like I said in previous lectures, we already have a lot of pre-trained models and you do not need to build anything from scratch, right? But knowing the transformer architecture will help you build any model from scratch in case if you need to build, or it can help you to understand how the pre-trained model works, right? So why are we learning transformer? So if you notice in this diagram, AI, artificial intelligence, this is the broad term. So the objective of artificial intelligence is to find patterns from the given data. So we are trying to make the machine so intelligent that it can behave like a human. So how do we achieve that? How do we give intelligence to a machine? So to achieve this, we have machine learning, deep learning, NLP, natural language processing, generative models, right? So we have different mechanisms available to make the machine intelligent like a human. And the objective of generative models is to generate something, as the name suggests. We use generative models mostly on the unstructured data. The model can generate either text or image or text or image, right? That's a multimodal combination. So the main algorithms inside these generative models are VAE, that is variational autoencoder, and the second one is GAN networks, that is generative adversarial network, and the third one is transformer, right? Those are the architectures behind these large language models. So why are we learning transformer, right? So we will know how these large language models are built and the architecture behind these LLM, that is GPTs or any other pre-trained models, right? In generative models, 90% of the models are built on top of the transformer architecture, right? And I also want to clarify here, not all the models are built using transformer architecture, right? For example, deepfake video generation is built on top of GAN network. But majority of the generative AI models are built on top of the transformer architecture. So that is why we are trying to understand transformer architecture so you can understand how these large language models work internally, right? And in 2017, Google released a paper and the architecture was very well explained. And before that, Google released a model called BERT. BERT is bidirectional encoder representations from transformers. And this was the old model. But as you know, we have GPT-1, GPT-2, GPT-3, GPT-4. All these GPTs, they are built on top of transformer architecture. So transformer is a part of generative models, which is part of neural networks and which is part of machine learning and which is part of artificial intelligence. Now let's see what is a transformer. And you can see here, this is the architecture of the transformer. And we are learning both encoder and decoder, but GPT is only decoder. Some models are only encoder based and some models are only decoder based. For example, BERT, right? BERT is only encoder based model, whereas GPT is generative pre-trained transformer. GPT is decoder based model. But let's learn both encoder and decoder model so you will understand the entire transformer architecture. So first let's start with encoder and then we will move on to decoder, right? So this is the encoder piece, and as I said, BERT is encoder model. Assume you are using BERT model as it is an encoder based model, that is a transformer based language model, and BERT uses a vocabulary of 30,522 tokens. These are unique tokens or words, and they achieved through word piece tokenization, which breaks words into subword units. But these 30,522 unique tokens or words are the most common English words. So as I said, these are only the most common words. We may have happiness in the list, but the model is intelligent enough to understand the opposite word of happiness is unhappiness. Even if unhappiness is not present in this 30,522 tokens, the model is intelligent enough to understand the opposite word of happiness is unhappiness, right? And as you can see in the diagram, the first thing that we are doing here is we are providing an input to the model. Here in our example, we are considering BERT model, which has a vocabulary of 30,522 unique words or tokens, right? So first we are providing the input, and this input will be converted to input embeddings, right? So assume this is the input to the transformer. We are giving this is a generative AI course. So assume this is the input sequence that we are providing to our BERT model, and then this is just one sentence, but in real time we may have several sentences as well, right? I just took only one sentence as an example so we can understand the architecture behind the transformer. Okay, so once we provide this input to the model, then the next step is tokenization, right? So that is, it will convert the input into tokens. So our input is, this is a generative AI course, and it will convert into tokens. That is, this is a generative AI course, right? We have 6 tokens, and once the tokenization is done, the next step is token IDs. So we are trying to represent each token with a token ID. This token ID is nothing but the position of the word or token in the entire vocabulary of 30,522 unique words, right? For example, let's consider the word this, right? So this may be present in the entire 30,522 unique words list, somewhere maybe in the 10th word or 100th word or 1000th word, right? Somewhere there will be, somewhere this word will be present. So assume the word this is present somewhere here, 2222. Okay, this is just an example. So assume these are the positions of the input tokens. This is a generative AI course, right? So that is, the token ID can be anything between 1 to 30,522. So just assume the position of the word this is 2222, and the position of is 300, position of a is 987, and the position of the word generative is 1001, and the position of the word AI is 586, and the position of the token codes is 898. Okay, so that is how we represented each token with a token ID. In real time, we will not have just one sentence, right? We may have multiple sentences as well as the input data. So how does the LLM know the starting and ending of the input, right? Input can have multiple sentences too. So how will the LLM know when we have multiple sentences, and what is the starting sequence and what is the ending sequence of the input, right? So that is why we will take special tokens. Okay, so here we are trying to add special tokens for our input. As a human, we can understand the period at the end of the sentence says it's end of the sentence, right? But how will the model understand that the sentence ended? That's why we are adding these special tokens. Okay, so if you notice here, we added CLS as a starting special token and SCP as the ending special token. So CLS means classification. This is input starting, and SCP means separator. This means input ending. And assume this is how it looks after adding special tokens. And you may have some question. For example, let's say if any of these words are not present in the 30,522 vocabulary list, right? Then what happens? The LLM is intelligent enough to understand other related words. For example, happiness and unhappiness, right? So if happiness is present in the list, whereas if unhappiness is not there, the LLM will be intelligent enough to understand the related words, and then it will get the token ID of happiness, right? So why are we adding these tokens? Because the model can understand only numbers, right? So what did we do so far? We represented our input as tokens, and we added these special tokens as well, right? And the next step is to convert our input tokens into embeddings, right? So this is our input, and we are trying to convert into input embeddings. And these embeddings are generated using ANN, artificial neural network architecture. So we use feed forward back propagation network to generate these embeddings. We'll pass the entire input tokens, and we will get the embeddings for every single token. Okay, since we are using BERT as an encoder model here to explain this architecture, and each model will generate a fixed dimensional embeddings for each token. In case of BERT, it generates 768 dimensional embeddings for each token. So 102 will have 768 dimensional embeddings, and 2222 will have 768 embeddings. Similarly 300, 987, and all the way to 6005. Each one will be represented as a 768 dimensional embeddings. So that is what will happen once the input is converted to input embeddings. And we have total 8 tokens. So we will have total 8 embeddings with a vector size of 768. Right? That is, every embedding will be of size 768 dimension. So now what we did, we converted the text into embeddings of size 768 dimensions. And if you notice here, these word embeddings, they are not random numbers, right? They are arranged in such a manner that similar words will come closer together, okay? That is, in 768 dimensional space, it's trying to arrange all the 30,522 words that have contextual meaning, right? Since we cannot imagine 768 dimensional space, for example, let's take only 3-dimensional diagram so we can visualize, as we cannot visualize 768 dimensions, right? If you notice here, we have sky, machine and wings, drone, airplane and eagle, right? So if you take here, this word drone is very close to sky, wings and machine, because drone has wings and drone is a machine and drone can fly in the sky. So this word has a contextual meaning. That is how the close words are trying to stay together, right? Similarly, if you take eagle, this is very close to sky and wings. Eagle can fly in sky and it has wings, but eagle is not a machine, right? Similarly, let's assume if you have ostrich here, ostrich is very close to wings and sky, but ostrich will be very far away to machine because ostrich is not a machine. So these word embeddings represent which words are together out of the 30,522 unique vocabulary list, right? So now we understand these embeddings. So for every single token we have 768 dimensional representations. Now let's see the architecture diagram. We have input and we converted that to input embeddings with a vector size of 768. And now if you see the diagram, next thing what we are doing here, we are trying to add positional encoding to the input embedding. You see the addition operator here. So we got 768 vector size of input embeddings, and next thing is we have to identify how to find positional encoding, and then we can add these two. So now let's see what is positional encoding. So as a human, we understand the position or context of each word with respect to each other word, right, in the input sequence. But how will the model understand the position of each word with respect to each other word? So to understand the context of a word, the order of the word is important, right? So which order the word belongs to in the input sequence. And to understand the order of the word, we have to add a technique called positional encoding. So the objective of positional encoding is to add position information of each word. But how can we do that? So maybe you can try to add an index to each token like 0, 1, 2, 3, 4, 5, 6, 7, etc. But this is just one sentence, right? In real time we will have petabytes of data, right? So this indexing may not be a good idea, right? So what else we can do to add position information to each word or token? We need some function which can generate a continuous index or continuous number, right? That is, 0th index stands for CLS, the first index stands for this, and second index stands for is, etc., right? And if the index repeats, then we will be confused, right? So the index should not be repeated and each token should have a unique index, right? So we need some continuous unique numbering system, right? So if you use index, it may not work, because if you have huge amounts of data, then this indexing might not work. So the solution they have given is to use sine and cosine functions to generate these positional encoding. That is, continuous unique numbering systems can be generated by using sine and cosine functions, right? And you can refer this If you want to deep dive, I found this very useful. In this they explained using GPT, so you will see 512 dimension, right? But we are using BERT, so which is 768 dimensional. So let's go to the positional encoding. Right? So what is positional encoding? So with the positional encoding, the model not only knows the context of the word, and it also understands the position information of the word. So what is positional encoding? We want each word to carry some information about its position in the sentence, right? In the input sentence. And we want the model to treat words that appear close to each other as close, and words that are distant as distant, like we saw in the other example, right? And we want the positional encoding to represent a pattern that can be learned by the model, right? In our example, as you can see, the word AI is very close to the word course, and similarly the word this is very distant to the word course, right? Here you can see the input sequence is your cat is a lovely cat. So that is the original sentence, and they are trying to apply positional encoding here. So here they are using GPT, so that's why you are seeing 0 to 511, because each model will have fixed vector size, right? So that is how we are trying to get the positional encoding by using sine and cosine trigonometric functions. But you might think like, why we need trigonometric functions? Because sine and cosine functions can generate continuous numbers, right? Because these trigonometric functions like sine and cosine naturally represent a pattern that the model can recognize as continuous. So relative positions are easier to see for the model, right? So this is how it can generate the continuous pattern. And if you notice here, we only have a vector size of 4, right? This is not 512. So let's take the simple example so it will be easy to understand, right? So these are the formulas. This is position encoding PE of, you'll have to pass position comma 2i. So I is the index, right? Equal to sine of position divided by 10,000 to the power of 2i divided by d model. That is the dimension of the model. Here we are taking d as only 4, right? If it is BERT, you already know it is 768, whereas if it is GPT, you know it is 512. So each model will have fixed d, that is embedding vector size, right? This is how we'll calculate positional encodings by using sine and cosine functions. Here POS means position of the word, and I is nothing but either sine of 0 or cosine of 0. So you can see sine and cosine, and again for the first index sine and cosine, right? So for each index 0 and 1, we'll do sine cosine, right? This is how we'll calculate the positional encoding. Here sine and cosine as a pair we are trying to calculate for each embedding. Let's assume for position 0, right? So this is position 0, position 1, position 2 and position 3, and the I value 0, 1, 2, 3, right? So you have to replace for the first position, so that is 0. So you have to replace with 0, and the value of I is here 0, and again 0 here, value of I is 0. This is sine cosine, one pair. You calculated sine cosine at the 0th index, and the next one is sine cosine at the first index, right? So the index value will change. So that is how we calculate positional encoding. So similarly, if you have a dimension of 768, so you will see a pair of sine cosine, right? So total it will be 768 divided by 2, right? So that many pairs you will see sine cosines, right? So that is how you will calculate the positional encoding. And now let's go to this diagram again, and the next step is, once we have positional encoding, we are trying to add this positional encoding with the input embedding. So finally we will get embeddings along with the positional encoding, right? Now with this positional encoding, the model knows the position of each word and which word comes closer to each other word, right? So is AI is closer to course word, or AI is closer to this, or AI is distant to the word this, right? So with this position encoding, the model is now intelligent enough to understand the position of each word and which word come closer to each other word. But is this sufficient? We also need to know how each word is related to each other word, right? So that is the correlation, right? That is the relationship between each word with respect to each other word. How this is related to ease, how this is related to a, how this is related to generative, how the word this is related to AI, or how the word this is related to course. So similarly, ease is related to this, etc. Right? So each word, what is the relationship of each word with respect to each other word? Right? For example, instead of this is a generative AI course, let's assume we took this input sequence as the input to our model, right? The girl is running, she is going to school. She eats apple every day, she has an Apple phone, right? So even after using positional encoding, the model still doesn't know the context of a word in a sentence, right? If you see here, how does the model know that she refers to girl, right? As a human, we know the girl is running, she is going to school. So we know she refers to girl. But how will the model know? And also, if you see in the second sentence, one apple refers to fruit, right? And the another apple refers to Apple phone. So same word apple with different meanings, right? So how will the model understand? To make the model understand, we have a concept called attention, right? So that is the main reason why the artificial intelligence is very popular, because of the attention concept. So attention means trying to understand every word with respect to each other word in the input sequence. Okay, so the whole objective is, for every word we will calculate attention, and all the values that the attention generates will be between 0 to 1, because that is a probability, right? So positional encoding is to add position information, that is the order of the word, right? The objective of attention is how every word is related to every other word in the input sequence. This is just one sentence, but if you take these sentences, the model will get confused. The model cannot understand that she refers to a girl, or apple refers to fruit here, and apple refers to a Apple phone here, right? So that is why we need to understand the relationship between each word with respect to each other word. So the objective of attention is how every word is related to every other word. So that's how we are preserving the context, right? And this attentional calculation is computationally expensive, right? But let's try to understand how we'll calculate the attention, right? So like I said, the attention score will be between 0 to 1, and which word has the highest attention score, that will indicate the relationship between those two words, right? So now let's see how to calculate attention, right? So we have query matrix Q and key matrix K and V, that is a value matrix, right? So we have three here in this formula. For example, let's try to calculate attention for the word this, right? So like I said, we have query matrix, key matrix, and value matrix, right? So embeddings plus positional encoding of word this will be multiplied with query matrix, then we'll get query vector. And similarly, embeddings plus positional encoding of the word this will be multiplied with key matrix, then we will get key vector. And similarly, embeddings plus positional encoding of the word this will be multiplied with value matrix, then we will get value vector. And the attention score is query matrix multiplied by transpose of key matrix divided by dk, and we'll multiply this with value vector, and we'll pass it to softmax, and this softmax is for normalization. So if you get the big value, we'll try to normalize using softmax, right? So that is how you will get the value between 0 to 1 as an attention score. So this is the formula for attention score. So now you know the transformer is powerful because of the attention concept, right? And the query matrix, key matrix, and value matrix, these are fixed for each model, right? So all words query matrix, key matrix, and value matrix will be the same, so they are fixed for each model. And the matrix values are calculated using neural networks, so that is out of the syllabus here. And then we will apply this softmax, so we will always get a value between 0 to 1. Go back to this article that we were referring before. Let's go to the self-attention section. So here you can see what is self-attention, and this is the formula they're trying to apply. And the input sequence is your cat is a lovely cat. So here we are trying to calculate the attention score for each word with respect to each other word. That is how the word your is related to the word your, how your is related to cat, how your is related to is, how the word your is related to a, each word with respect to each other word, how your is related to every other word in the input sequence. And if you see here, so let me zoom so you can see, and if you notice here, it is 0.2, 0.1, 0.1, 0.1, 0.1 and 0.1, right? That is how we are trying to understand how each word is related to each other word in the input sequence. Whatever the word has the highest attention score, then those two words will be closely related in the input sequence, right? And if you notice here, if you add the attention score row wise, then you will get the value of 1, right? Now let's see how to compute self attention, right? And if you notice here, this is of size 6 by 6, right? And they are using GPT model, that's why the vector dimension is 512. We are doing query times transpose of key matrix, so that is why we are getting the 6 will cancel and 6 by 512. So by using this attention score, this will solve one word multiple value problem, right? That is, apple is a fruit or apple is a phone, right? So you can easily understand the relationship between each word with respect to each other word. And once you have the attention score, the next step is we're trying to add and do the normalization, right? So we are normalizing by using softmax here, right? So that is how you can calculate the attention score and solve this problem whether apple is a fruit or apple is a phone. So attention is all you need. And if you want to deep dive on attention, this is the paper. Let me take you there. Attention is all you need, right? So this is the paper. You can deep dive if you are more interested on how we are calculating the attention score, right? But the objective of attention is trying to understand the relationship with each word with respect to each other word in the input sequence. So that is how it generates or predicts the next word in the sequence, right? And without attention score, these models cannot predict the next word, right? So meaning it generates the nearest probability or related word, right? And let me ask you a question here. In this, she eats apple every day. She has an Apple phone, right? So the token ID of apple, is it the same or different? So if you notice here, the word apple will have the same token ID, right? Out of 30,622 unique vocabulary list, the word apple will have the same token, but the positional encoding will be different, right? It will be different for the word apple here, and the positional encoding for the apple is different, right? But the token ID will be the same. And how will the model understand one is fruit and the other one is phone? Because of the concept of attention, right? Alright, so we saw once we pass the input sequence, how we are generating the input embeddings, how we are generating the positional encoding, and once we add, we are getting input embeddings with positional encoding. And then we saw attention, and we understood how to calculate the attention score and how to normalize it by using softmax. Right, so that is what is encoder part, and in the coming lecture we will see decoder side as well. All right, thank you.